Chemistry 3202, Course Overview Review. Okay, we're starting a new unit here. This is Unit 3, Thermochemistry, Section 1, Lesson 1, Temperature and Heat. Here we go. Temperature and heat dealt with on page 626 of your textbook. Make sure you go have a look. And here are a few related questions. You might want to give a try and check them out. And if you have any questions with these, let me know. Or check them out with the online tutor, which is free. Don't forget to check out the online tutor. Here we go. Here are the outcomes for this, this lesson. Okay, the branch of chemistry, I guess, that deals with energy changes is called thermodynamics, or the branch of any science, I suppose, because you can deal with thermodynamics in physics as well. So it's thermodynamics, and in our case, we're going to be looking at the chemical aspects of thermodynamics, which is going to be thermochemistry. All right, and thermochemistry then is going to be the study of the exchange of energy in chemical reactions, physical processes, nuclear reactions as well. Okay. So here we go. Some typical examples. We can look at energy exchange in a physical process. So in this case, we could look at, for example, the melting of ice. There we go, H2O solid, so that's ice. And in order to turn ice solid into ice liquid, we have to put energy in. Of course, we can do this by putting ice in the palm of our hand, and the energy would be released from our hand into the ice, and of course it would disrupt the crystals here and cause the water to liquefy. All right? So in this case, we can see that energy is going in here. The energy is going in to cause the physical change of producing liquid water. Now we know that this is a physical change because no new substances are formed. All that's happened is we had a change in state. So if we want to get the H2O solid back, well, it's easy enough. Take the energy out that we just put in. All right, freeze it. Put it in the freezer and take that energy out. So in this case, the physical change is indicated by the fact that it's H2O before, it's H2O after. All we've done was change the state. Some other physical changes we could look at, of course, would be boiling water, vaporization, condensation of water, which is the reverse of boiling or reverse of evaporation. We could look at sublimation, going from a solid to a gas, or deposition again, going from a gas to a solid. So these would be physical changes. Okay. Now in this particular process that's going on here, we're breaking up intermolecular forces of attraction. So we're breaking up the forces holding the solid together in the solid crystal state. And these were dipole-dipole forces. Hydrogen bonding is a big one here for ice, and London dispersion forces. Now remember, these are intermolecular forces from Chemistry 2202. Intermolecular forces are forces between two different molecules. They're relatively weak for the most part. And because they're relatively weak, of course, that's an indication here of how much energy is involved to pull them apart. Not much energy at all. In fact, we can melt ice in the palm of our hand. The heat from your hand is enough energy to disrupt these weak forces. Okay? Taking it a step further then, we can look at, say, a chemical reaction. And in this case, what we're going to do this time is we're going to make some water vapor. And when we make water vapor, of course, we have to break the bonds between the hydrogen atoms, we have to break the bonds between the oxygen atoms, and then we have to reform to create this new substance. So that's our cue then that this would be a chemical change. We get the formation of new substances. Bonds are broken, old bonds are broken, new bonds are being formed. So we see that this is indeed a chemical process by definition. So what's happening here is we have to break covalent bonds between hydrogen atoms, we have to break covalent bonds between oxygen atoms, and then we have to reform covalent bonds between the water molecules. Now remember from your Chemistry 2202 that covalent bonds are the strongest of all bonds. These are actual bonds between two different atoms, and they're very strong. When compared to these weak forces up here, there's hardly any comparison whatsoever. Look at this. In breaking these bonds, it's only taking 6 kilojoules of energy. These are very weak forces. In breaking these bonds and reforming these bonds, look at all the energy that's involved in the changing of these bonds. It's a lot more energy than it would be just in that physical change. Okay, so in terms of looking at the energy, physical changes generally involve the least amount of energy. And in this case, it works out to be almost 48 times more energy than a physical change. So that's significant. It's a significant amount of change. Now, if we take that a step further and we go to a nuclear change, what we're looking at here in nuclear changes is changes in the nuclear makeup of a compound. And we know that what's going on over in Fukushima, Japan, and Chernobyl back in the 1980s was the meltdown of a nuclear reactor. And in that case, tremendous amounts of energy being released, and it takes a long time. It's taking them forever to try and cool down that reactor and trying to manage all the energy that's being released. In this case, we know it's going to be nuclear changes because we recognize isotope notation. Once again, that's something from Chem3202. We can see that the isotope notation is showing us the mass number and the number of protons here. So anytime you see this isotope notation, generally we would only write that if we're talking about nuclear changes. Now look at the energy that's involved here. 10 to the power 10. Like, that's phenomenal. That's a tremendous amount of energy. And what we're saying then, that enormous amounts of energy here, and this is why we like to use it in nuclear power plants, because all that energy, rather than burning coal to create heat, what they're doing is they're using a nuclear reaction to produce a tremendous amount of heat, and that heat is used to boil water to make steam to turn turbines, and they make electricity out of all that steam. So a tremendous amount of uranium, a very little tiny amount of uranium is going to produce a tremendous amount of energy, and that's why nuclear reactions are so looked upon so favorably, because they involve a tremendous amount of energy. Okay, so when we look at this, we want to be able to look at some examples here. And what have I got done here? Okay, so we're looking at this and we're saying, okay, what type of chemical reaction are we looking, or what type of process are we looking at here? We're saying the reaction between propane and oxygen to produce carbon dioxide and water vapor. Well, that's going to be a chemical change, isn't it? Because we're taking bonds in propane and oxygen, breaking them down, and we're making new substances. So these would be chemical changes. Another example here, okay, icicle melts in a person's hand. All right, well, that's the melting of ice. That's physical. We can always get the ice back. Heat is used to decompose limestone, that's calcium carbonate, into carbon dioxide and calcium oxide. New substances are being formed. That's chemical. Here's another example. When sodium hydroxide is dissolved in water, there's a rapid increase in temperature. Well, that's going to be a physical process because we're simply looking at the dissolving of sodium hydroxide in water. And in doing so, if we want to get the sodium hydroxide back, all we have to do is evaporate the water. And this process of dissociation here, that's what we're measuring, the energy that was released during dissociation is going to be given back when we recrystallize it. All right, all we have to do is evaporate the water. So that's very much a physical change. And finally, sunlight is a result of the fusion of hydrogen on the surface of the sun to produce helium. Well, that's a change at the atomic level, and that's going to be a nuclear change. That's a tremendous amount of energy. There we go. Okay. With this now, we need to be able to refer to what we're talking about whenever we talk about energy, because if you look back here, we can see that in some examples, energy is on the left-hand side, energy is on the right-hand side here. And we need to be able to talk about the process, you know, what's going on. Is it a physical process? Is it a chemical process? Is it a nuclear process? And we want to be able to refer to what's happening to the energy. So in this case, energy is coming from somewhere. In order to melt that ice, you put the ice in the palm of your hand. Well, now the palm of your hand is involved in this process because it's releasing the energy. It's providing the energy source for that process. In this case here, if we're going to fuel up a space shuttle rocket, we use liquid hydrogen and liquid oxygen. And the tremendous amount of energy that's released, of course, in the production of water vapor is what's going to propel that shuttle up into space. So now all of a sudden, we got this chemical reaction, which is our process that we were studying. How much energy are we getting? And therefore, where's this energy going? Right? It's going out into another, you know, causing the rocket to go up in space or whatever. And in this case here, we're looking at the actual process of a nuclear change. Where's all this energy going? What are we using it for? Is it a nuclear bomb, or is it a nuclear reactor, etc.? So we want to be able to look at this and be able to look at every process that we're studying from a perspective of the system and its surroundings. The system is going to be referring to the process. What is it we're studying? The melting of the ice, the nuclear fission reaction, the combustion of hydrogen. That's our process, the dissolving of sodium hydroxide. We're looking at how much energy is involved in that process that we're studying. The surroundings is going to be referring to anything that's going to be in direct thermal contact with our process, anything that's going to be able to absorb the energy or release the energy. So for instance, as I put that ice cube in my hand, I'm studying the melting of the ice. That's my process. So the melting ice is the system, and the surroundings is where is that system getting its energy to do its melting? Well, it's getting the energy from my hand. My hand is in contact with the ice cube, therefore my hand is considered the surroundings. All right, it's got to be in direct thermal contact. Okay, here's a few examples then. So together, the system and the surrounding makes up what we call a universe. Now, lots of times we think of a universe as being that great big colossal thing as we gaze out on the night sky. Sure, that can be a universe. But for us, when I'm melting ice in my hand, I actually have a universe in my hand because I'm studying the system and my hand is providing the energy. That's the surrounding. So in a sense, by definition, if a system and a surroundings is what makes up a universe, then my hand, I have a universe in my hand. So here's another example. This is a case where I'm going to say, okay, let's get rid of me touching it all together because we don't want to do chemical reactions and whatnot in our hands. So let's put it in a reaction vessel. Let's put it in, say, a styrofoam cup or an insulated container. And in this case, if I have a chunk of ice in some water here, what we're going to do is measure the change in temperature of this water, because what's happening is as this ice cube melts, it's taking the energy away from the water. The water now has replaced my hand. Before, the ice was getting the energy from my hand. Now what's going to happen is the ice cube is going to get the energy from the water that it's in, and therefore we're still studying the melting of ice, so that's my system, and the surroundings now is going to be anything that's in contact with the ice. Now you might say, well, why not the thermometer? Well, technically, yeah, but the thermometer is in contact with the water. It's not in contact with the ice. The styrofoam cup is in contact with the water. It's not in contact with the ice. And anyways, the styrofoam cup doesn't absorb much energy. So, we're going to make a few assumptions here. But in any case, to keep it simple, we're going to say anything that is the surroundings has to be in direct contact with the system. So in this case, it's only the water that's in direct contact with the ice. So there we go. Now again, the connection between the system and its surrounding is if it's going to be in direct contact, then heat is going to flow from one to the other. So when I had this ice cube in my hand, the heat was flowing from my hand to the ice. So the ice was the system, that's what I was studying. My hand was the thing supplying the energy for that process. So my hand was the surroundings. Okay? So whenever they ask you to identify the system and surrounding, remember that once you identify the system, only the things that are in direct thermal contact with the system are considered the surroundings. Okay? So therefore, with this idea then, we have to come up with the idea that heat is a fluid thing. Heat is able to flow from a system to a surrounding. So when heat flows into the system, we're saying that the system is absorbing energy. We call it going into the system, endothermic, into the system, endothermic. All right? So we say that it's an endothermic system. So here we go. Energy is flowing into the system. So if this was a piece of ice, energy would be flowing into the ice cube, and in the case of me having it in my hand, the energy would be coming away from my hand. Now, I never refer to my hand in this energy exchange, or I rarely do. Whenever we refer to energy changing or heat flowing, we always like to reference it in perspective from the system. What's happening to the system? Because it's the system that we're studying. Okay, so in this case, we want to say that heat flows from the system. We would call that an exothermic process. So if we had a hot object, like a hot piece of metal or something, then if we put that in our hand, or if we put a hot object in, say, a cup of water, then that hot object is going to release its energy, and in this case we say the system now is losing its energy, so we refer to that as an exothermic change with respect to the system. Okay, so anytime we're going to refer to a heat transfer, we always like to refer to it with respect to the system. Okay? And the idea being here, of course, is that it's an energy transfer from one to the other. So in this case, if the system is cold, indicated by the blue, it's going to be in contact. So as these molecules are vibrating and colliding with one another, the energy is going to be transferred from the warm body to the cold system. All right? Okay, one sec here now. Okay, with that said then, we have to refer to the different types of systems we might have. Now again, we're studying the system, not the container that it's in. A lot of people get confused when they talk about systems and whatnot. We like to refer to the container, like a cup, like a coffee cup or a styrofoam cup or a thermos bottle. All right, we would refer to that as the container, of course, that it's in. But when we refer to systems, we want to look at what's going on with the system. So quite generally speaking here, we said a closed system, by definition, is something that's open to the flow of energy, but closed to the flow of matter. So in that we mean that energy, it can get warmer or it can get colder, right? The system can gain energy and get warmer, or the system can lose energy and get colder. But the amount of material in the system is never going to change. We're not going to add any extra. We're not going to take any away. So in that process of heating up or cooling down, the amount of material of the system stays the same. I got a few examples to show you now in a second. The second type here, of course, is referred to as an open system. So in this case, it's a system that can either warm up or cool down, but in the process of warming up or cooling down, some of it is lost. Okay? So think about me having an ice cube in my hand. Even though it's not in a, there's no cap over it, I don't have my hand in a big plastic bag or anything like that, I just have an ice cube. We would refer to that as an open system, because the ice cube is gaining energy from my hand, and as the water melts, it can also evaporate. So at the end of that process, some of the water is going to escape into the environment, the atmosphere. So in that sense, it's an open system because, yes, it gained energy, it warmed up and melted, and some of the water evaporated during that time frame. Okay? That's an open system. If I took a closed system, let's say I took a spoon that was warmed up in the dishwasher, or a spoon that was very hot because it was in hot water for a period of time, and I take that very warm spoon and I put it on my hand. My hand is going to start to warm up because that spoon is releasing its energy as it cools. When that spoon completely cools off, it's going to have the same mass before as it had after, because the spoon is not going to change. None of it is going to escape, although it did exchange energy. So that would be considered a closed system. An isolated system is one that's closed to both the flow of energy and the flow of matter. And we're going to talk about that one now in a sec. So here we go. Let's do some more particulars on a closed system. So this guy is open to the flow of energy but closed to the flow of matter. So this could be an example, of course, of a gel pack, freezer pack that you put in your lunch bag when you go to school during the day. And what happens, of course, is the freezer pack keeps your lunch nice and cold. And it, you know, when you're finished with it, you can easily go home and put it back in the freezer and refreeze it so that it can do its job again tomorrow. All right? The exchange of energy there, the heat pack cools off, warms up, cools up, freeze, refreeze. It can get an exchange of energy. And in a sense, the contents of the fruit pack, or the cold pack, sorry, is in a closed container. It doesn't get a chance to evaporate because it's capped off and nothing can get in or nothing can get out. All right. So the gel packaging, or the gel, stays in the plastic packaging, so the amount of mass does not change. So in a sense, we can look at this and we say, well, it doesn't necessarily have to be a capped container, as we said before. Here's another example. If I take a piece of hot aluminum, a chunk of aluminum, and throw it in water, and I can measure the change in energy of the water, it's the cooling off of the aluminum that I'm studying, so that's my system. The aluminum is releasing its energy, so it's an exothermic cooling process. It's releasing its energy to the water. The water's going to warm up. And at the end of this process, the chunk of aluminum has the same mass before and after, so it's going to be a closed system, even though I don't have any cover on the top here. Because I'm not studying what's happening to the water, am I? The water is now my surroundings. What I'm studying is the aluminum. Okay? There we go. So some examples here, of course, would be like a bottle of pop that we put in the fridge. The bottle of pop is warm when we buy it at the store. We stick it in the fridge, it cools off. We didn't lose any pop, we didn't gain any pop. It's capped, it's stoppered. None can get out, none can get in. Right? A reaction taking place in an aqueous medium, like say when we put an acid-base reaction, of course, where the amount of liquid stays the same. We'll talk about these more when we get into calorimetry, by the way. And here's another one. This would be the reaction of NO2 to produce N2O4. And in this case, we had to put a cover in here because if we never, the gas would escape, and then that, of course, would be a loss of matter, and then it would be an open system. So by putting a plug in this one, in this case, it's essential that it's capped off because we don't want any of this to escape. There we go. So that's a closed system. Here's some examples of an open system. This is a system that's going to be open to the flow of energy and matter as well. And in this case, we could look at, say, a glass of water on the container. It's not covered or anything. And as the glass of water cools off or warms up, depending on what the temperature outside is, the water evaporates, and of course now some of the water is lost. So in this case now the water is the system, because that's what we're studying. And in this case the water evaporates, therefore we have a loss of matter. So it's all a matter of determining what you're reacting with. In this case we can look at a cold pack. Now the way this particular cold pack works is it's a pouch of water, and inside this pouch there's another pouch of dry chemicals, and the dry chemicals is ammonium nitrate. And what you do is you pinch the pack in order to break open the dry chemicals and get it to mix with the water. Now it's the dissolving process of the ammonium nitrate that absorbs all that energy. That's what makes the water get really cold, and when they put it on your swollen ankle or whatever, it feels nice and cold and it cuts down on the swelling. Well, the process here is the actual dissolving of the ammonium nitrate. In that process of dissolving, the ammonium nitrate now dissolves into the water, and what we're finished with is a new solution. And the solution itself has a greater mass now because it's now mixed with ammonium hydroxide. So we've had a change of mass here. The process of dissolving that ammonium nitrate has caused the mass of the surroundings to increase. So because we've had a loss of mass, therefore this is an open system, because it's the ammonium nitrate dissolving that we're studying and not the bag. It's not the pouch that we're studying. It's what's happening inside this pouch. And because there was a transfer of mass from the system to the surroundings as well as a transfer of energy, then this would be an open system. Okay? Again, more on that when we start looking at calorimetry. And you'll see when we do calculations why we would refer to it as an open system. So in this case, there's an exchange of mass between the system and the surroundings. So here we go. So in this process of absorbing the energy, of course, these ions now are in the surroundings, and they've increased the mass of the surroundings, because not only is the surroundings water, the surroundings is water plus these ions that are now floating around. Here's an example of a warm pack, I guess, sodium hydroxide, that would be placed in water, and this produces a lot of energy in that process. So this would be endothermic, and the sodium hydroxide would be exothermic. And I'll write that in here. That's endo, and this guy here would be exo. Okay. An isolated system would be one that everything is just perfect. It's closed to the flow of energy. Nothing can get in, nothing can get out, and it's closed to the flow of matter. In an ideal world, this really doesn't exist. Okay, because no matter what you have, at some point the container is going to be in contact with a tabletop, the outside world. Energy is going to be able to seep out of the container somewhere, wherever there's a seal to the outside, wherever there's a stopper to try and close the inside from the outside. In that particular point, we're going to have thermal contact. However, we can get something that approximates or gets very, very, very close to an ideal world. And in this case, we would use what's called a Dewar flask. And a Dewar flask is like a thermos bottle. Okay? And what happens here, of course, is the thermos bottle has a vacuum seal here. And the vacuum is nothing, is it? That's where all the matter has been sucked out. And the only way energy can transfer from one body to another is if we have thermal contact. Molecules have to collide so that the energy can be transferred. If we have a vacuum between the inside and the outside, that the energy of these molecules is going to collide with the inside of the container, but the energy is not going to be allowed to transfer through here because there's nothing there to propagate the energy. It's a vacuum. So ideally, there's not going to be any transfer of energy. Now the problem is, of course, where this vacuum seal stops here, we have to somehow have a container where we can pour the stuff in and out. So right here, there is no vacuum seal. There is no vacuum seal here. So anytime this hot coffee collides with this up here, or even the air that now is very, very hot, as this hot air collides here, we're going to get collisions, and this is going to vibrate a little faster, and we're going to lose the energy to the outside. So there is going to be a little bit of bleeding of the energy, I guess, through this particular small spot right here. But anywhere there's a vacuum seal, there's not going to be any transfer. So in this case, we've minimized transfer tremendously, so therefore there's not going to be any transfer inside, outside. There we go. So that would be an isolated system. And we said this is an ideal world. It doesn't really exist. Okay. Why would we want to study it then? Well, we like to study things and say we're in an ideal world to try and minimize any other things that might come on and interfere with what we're studying. And more on that when we talk about calorimetry. Okay, well, with this energy transfer, I guess, with all the different collisions and what's going on, we have to consider, well, what's going on with the particles. And we're saying when a particle has energy, it basically has three forms of motion. It has a vibrational motion, which is simply when it's vibrating back and forth. Okay, like someone shivering, you're vibrating back and forth. And this was what would represent solids, I guess. Solid molecules, they don't look like they're moving, but at the molecular level, they would be vibrating. They would be shivering in one spot, and they would still be moving. And we know this is true, of course, because when we heat up a solid, it begins to expand, it gets bigger, and therefore what's happening is the vibrational energy increases and it starts moving larger and larger and larger, and the solid material starts to expand. The second type, of course, is rotational, where the molecules are spinning now. Not only are they vibrating, they're spinning, and what's happening, of course, is they're spinning around and around, so they would have more energy to do that. And finally, we have what's called translational energy, and this is where the particles actually have enough energy now to start moving from point A to point B and start moving around. And you can envision this as a liquid. Liquids, of course, the particles are moving, spinning, and there's, we see currents of water moving around, and as we stir the water up, the energy gets dispersed because the molecules with these high energy are moving to different parts of the container. We take that to extreme. If we give them a lot of or a tremendous amount of energy, now these guys start moving independent of one another, and they start zinging around as gases, right? They're moving all over the container, all over the room, and there we go. So three types of energy, and we say then that if this energy is depending on the speed that they're moving, then we refer to this energy as kinetic energy. It's energy of motion. So kinetic energy is energy of motion. Now, if we looked at a thermometer and say, well, how can we measure this? How can we measure this energy? And it's very difficult to do because we really can't see the particles moving. However, we can see the effects of their movement. If I took a thermometer here like this, and I put it in a hot coffee cup of water, so if I put this in a cup of hot coffee here, all right, there we go. So hot coffee. And what we're seeing here is that as the thermometer goes down in the hot cup of coffee, the water molecules that are tremendously hot here start colliding with the walls of the thermometer. And as they collide with the walls of the thermometer, they start giving up their energy because there's a transfer of energy here. It's a collision, right? Transfer of energy. So what happens then is the mercury or the alcohol that's in this thermometer, it begins to pick up some energy, and it starts to get a little bit excited, and it says, hey, ooh, this feels good. And as the alcohol or mercury starts to increase its energy, what happens is they start to move faster and faster, and they're going to need more space, because the more energy they have, the more space they need for all this vibrational, rotational, and translational energy. The alcohol has nowhere to go but up. And as it continues to heat, of course, we see this energy that it's gained in its expansion. So when we measure the expansion of that alcohol up the thermometer, we're getting an indirect measure of the amount of kinetic energy that those particles would have. So in a sense, the higher the temperature of something, the more kinetic energy they have. All right, so let's go have a look at this. So temperature then is going to be an indirect measure of the kinetic energy. The more kinetic energy we have, the speed of the particles, we're going to say the more that alcohol is going to expand. The faster those alcohol molecules in that thermometer get, the more they're going to expand, the more they're going to move up. The more they've expanded means they're moving faster. They have more energy. So what we're going to say then is that temperature depends on the speed of the molecules. So temperature is proportional to the speed, so that if the speed of the molecules goes up, so too do we see that increase in temperature. The mercury or alcohol is going to rise up the thermometer. Likewise, if we increase the temperature of something, then that means we're going to make the molecules move faster. So everything is going in the same direction. If we slow it down, it cools down. If we cool it down, the molecules slow down. All right, so there we go. So temperature is proportional to the velocity or speed of the molecule. And we can see this, of course, we can visualize this by looking at the thermometer itself. Okay, if we had a digital thermometer, what it is there's a resistor at the end of that digital thermometer that can detect. It has a variable resistor depending on how excited it gets. It changes its resistance as it gets hotter or colder, and then the computer would detect a voltage change, and the voltage change would be then calculated to see what temperature that reflects. All right, so it's still based on the increasing or loss of energy. Heat, however, the difference between heat and temperature is an energy transfer between an object that's warm and an object that's colder. All right, so as a hot body is in contact with a cold body, the heat is exchanged. All right, so energy flows from the warm body to the colder body. And we can look at this and tell you the difference here. We can say if we had a brick, assume brick A and brick B were the exact same size. If brick A had 100 degrees, it was measured to be 100 degrees Celsius, and brick B was much colder, 50 degrees Celsius. What we're going to notice is that when we put these two guys in thermal contact, assuming there's no loss to the outside air and all that stuff, if there's any energy transfer, it's going to go from the hot object to the cold object. If we wait long enough, what we should see is that both bricks should end up to have the same temperature, and at that point we would say that brick A and brick B have reached thermal equilibrium. They have the exact same heat now. All right? So in terms of how fast this is going to take, if brick A and brick B were little tiny things, like two little tiny pebbles, then that wouldn't take very long, would it? Because they're not very big. If I had two great big enormous bricks or great big boulders, this energy exchange would take a much longer time to happen because it's not necessarily the amount of temperature it would have. It's because the bricks are so massive that they would be holding a lot more energy, and it would take a lot longer for thermal equilibrium to be achieved because the bricks were so big. So in terms of the temperature, we can say that what it is before and after, no problem. But how much energy was exchanged between these two bricks, that's another issue, because the amount of energy that was exchanged depends on how big the bricks were. Okay? So the temperature is proportional to the speed of the particles. Whether this brick it can fit in my hand or whether this brick has to be put in a pickup truck, they can both be at 100 degrees Celsius because they're both vibrating at the same speed. But clearly, that brick that I can put in my hand is not going to have as much energy as that great big chunk of concrete or brick that I could put in my truck. All right? So heat then depends on not only how fast the particles are moving, but how many particles are there. So heat depends on both mass and the speed of the particles. Here's another example. We got two objects. Think of these as being molecules. We've got a molecule here that's really tiny, not very massive at all, and we got this very, very, very massive molecule. They're both traveling at the same speed. Therefore, they have the same temperature. Which one has more energy? Well, it's going to be the more massive object, obviously, because that's going to burn more fuel. In order to keep this guy going at 100, because it's so big and heavy, it's going to require a lot of energy. This guy here, because it's so tiny, doesn't have to burn much fuel at all to keep it going at that velocity. All right, so the more massive you have, the more mass, the more energy it's going to involve. There we go. Same thing's true here. If I had a swimming pool, my little kitty wants to go out in the swimming pool, and it's very, very cold because the tap water is very, very cold. So I'm going to go out and take one mug full of hot, steamy water from the kettle, and I'm going to say, here, I'm going to throw that in the swimming pool. It should be warm now. Not really, is it? Because even though this has a lot higher temperature, the amount of mass here is not near enough to cause any change in this temperature, because there's so many more molecules. As these guys get thrown in here and start colliding, the energy is just going to be dispersed amongst these tremendous amount of molecules that are very, very cold. So this is going to have very little effect because it's not massive enough. There we go. Okay. A couple questions go along with this then. Distinguish between different types of energy changes. Well, we did that at the very beginning, so you can go back and look at that. Number two, for each description, describe whether or not it's system or surroundings and whether it's an open or closed system. Moisture condenses on a window. Okay, well, that's simply going to be a physical process because it's a moisture condensing, so we're taking water vapor and creating water liquid, and that's going to be very much exothermic because the energy is going to be released. And we can consider this a closed system because, you know, if we were in a closed container, depends on the conditions, doesn't it? And if it's a window, if your house is really, really tight, then the moisture can't get out. So we could somewhat consider this to be a closed system as long as nothing can escape. As long as the windows are all closed and there's no drafts in your house and your house is very, very tight. Okay, a marshmallow burns in air. Well, that's going to be the combustion of sugar because that's what marshmallows are. So that's very much a chemical process. And it's going to be an open system since once this stuff burns, all of the products, because it's burning in air, is simply going to escape to the outside world. And therefore, we're losing mass. So it's an open system. Crystals of potassium iodide are added to a beaker containing aqueous solution of lead-2 nitrate. A yellow precipitate forms and the temperature of the water increases slightly. Okay, well, in this case we're looking at the idea here that the potassium iodide is a chemical reaction, very chemical here indeed, and energy is being produced, so it's exothermic. And the reaction then becomes part of the surroundings. So for that reason, it's an open system. All right, so as we mix these guys together, we're throwing them into the water. And when the reaction's finished, of course, everything is mixed together, so we have an open system. And the last one, of course, we've talked about this, because we're doing it on your open hand, water can escape. so the system can escape. Here we go. Here's another question. It says we got two bundles of copper wire. They have different masses but the same temperature. What can you say about the average kinetic energy of the copper in each bundle? Okay, so here we go. We've got two bundles of copper wire. Let's say, for argument's sake, they're both at room temperature, 25 degrees Celsius. This bundle is 1 kilogram. This bundle is 2 kilograms. So we got twice as much mass here, half as much mass here, but they're at the same temperature. What can we say about the average kinetic energy? Well, in this case, the average kinetic energy is a measure of the speed of the particles. In other words, it's a measure of the temperature. So in this case, their kinetic energy average is going to be the same because they have the same temperature. What's different about them is the amount of energy that they have. The more massive bundle has more energy than the colder bundle because it's twice as much mass. Okay? There we go. So temperature depends on speed or velocity. Energy depends on mass and temperature. There we go. All right, short lesson. Be sure now to check with our online tutors here if you want some more background information on this. And don't hesitate now to try some of these questions and fire me off some discussion emails here, or check some of these with your tutor and they can help you out. All right, see ya.